Welcome to this presentation of Nichromet's extractive technologies. The last 7 years, Nichromet Extraction Inc. has been involved in a research and development program oriented towards problem-solving in extractive metallurgy. This orientation has been motivated by difficulties encountered with several refractory ores, either sulfides or oxides, when recovery of the metallic content was attempted by conventional approaches. Environmental considerations were also involved in this search for new avenues in extractive metallurgy, some existing processes being known for their very negative impacts on the environment, particularly with sulfur-bearing ores. Degradation either by hydrochloric acid or elemental chlorine was selected as the preferred approach to metals extraction. The reasons for this choice are the high reactivity of these agents towards metal oxides and the high solubility of the resulting salts. With few exceptions that can be corrected easily by ionic strength adjustments, such as with silver, lead, copper, and iridium, all chlorides of precious and base metals are very soluble in water. We now present the implementation of Nichromet technology with sulfides. Generally, sulfides are concentrated by flotation before being submitted to a metallurgical process for metals recovery. We proceed here in a similar fashion, and the starting material in our system will be a concentrate obtained from a sulfide ore. The oxidation of sulfides by chlorine proceeds easily, but results in a high consumption of chlorine. 8 atoms of Cl per sulfur if the oxidation proceeds all the way to sulfate, or 2 Cl per sulfur if the oxidation is stopped at the level of elemental sulfur. Since the sulfur in the sulfide concentrate will vary from 15 to 25%, it will be readily understood that chlorine oxidation is uneconomical. Been found that sulfur and other components, such as arsenic, can be eliminated from the sulfide concentrate by controlled oxidation of said concentrate. Controlled oxidation is not roasting. Roasting or burning of sulfides with free access of air has a well-deserved bad reputation from its very detrimental impacts on both health and environment. Also, roasting because of its high temperature can induce sintering of the ore and make it refractory to metal extraction. We have found that by diluting the air feed with flue gases, it was possible to maintain the oxygen content of the air feed to about 10% oxygen instead of the 20% in undiluted air. In that fashion, with a temperature control that does not exceed 600 degrees Celsius, the oxidation is complete and exothermic. That is, it does not fuel other than the sulfur in the concentrate, and leaves a solid residue with a very open structure, amenable to leaching. Besides oxidation of sulfur, important reactions take place during the controlled oxidation. In the presence of metal oxides, such as copper oxide, that are good catalysts, the initial sulfur dioxide is oxidized in part to sulfur trioxide that leads to sulfuric acid. Also, some of the arsenic, iron, antimony, and bismuth are oxidized to their higher valency, leading in the case of arsenic to the formation of ferric arsenate. This chemistry is complex and substantial. The sulfur dioxide stream resulting from the controlled oxidation contains solid particles, volatilized oxides such as arsenious oxide, and some sulfuric acid. This stream has to be cleaned before being released to the atmosphere. This involves two sets of operations, one for the arsenic-bearing components and the other for the sulfuric dioxide. We will deal with each of them separately. Extraction of arsenical compounds from the sulfur dioxide stream is done the following way. First, the hot gases from the oxidation reactor are circulated in a cool silica tower acting as a cyclone. In this tower, the sulfuric acid, particulates, and some arsenical vapors are condensed and washed out. These washings are oxidized by chlorine in the presence of iron to precipitate scorodite along with gypsum from neutralization by limestone. After cycloning, the gas stream is circulated through an impact dust collector, and then through an acid washing tower, where the last traces of arsenic are removed. This acid washing is also oxidized and neutralized with limestone, in order to transform all the arsenic in the form of a neutral and stable solid made of scorodite and gypsum. This solid residue, along with the solid collected from the impact dust collector, can be disposed of safely in sealed containers. With that approach, arsenical compounds are concentrated in solid form and can be prevented from being recirculated in the environment. Sulfur dioxide stream, now free of particulates and arsenic, can be disposed of by scrubbing with limestone using the technique developed for the control of sulfur dioxide in utilities companies in the United States. This well-proven technology, practiced on a very large scale, consists of scrubbing the gas stream with a slurry of limestone. The resulting calcium sulfide is oxidized in situ to hydrated calcium sulfate or gypsum. Clean gypsum is a secondary product used in large volumes for the production of Portland cement and the manufacture of wallboards. It can be disposed of safely in the environment without restriction. The water involved in those different steps is recycled, and there are no liquid effluents resulting from the arsenic control that are released in the environment. The controlled oxidation of the sulfides concentrate has led to an essentially sulfur-free solid with a rather open structure that is ready for the recovery of base metals. The first leaching is done with water in order to recover the soluble sulfates formed during the controlled oxidation. This first leaching is completed by a second one, using 5 to 10% sulfuric acid at 50 to 75 degrees Celsius. These two leachates are combined for metal separation, and the residual solid left is ready for precious metals leaching. The separation of metals calls upon collection of copper by cementation, followed by nickel, zinc, and cobalt recovery by specific ion exchange resins, and completed by lead precipitation as chloride. The pH of the resulting solution is then raised above 6 by limestone addition, and with aeration, the sulfates and iron are precipitated. The water can be recycled after sedimentation in a settling pond. Oxidized ore, depleted of base metals, is now ready for precious metals collection. In the case of gold and silver, this operation is conducted by chloridation of the substrate with added salt. 5% by weight with elemental chlorine at about 45 degrees Celsius. This chlorine is doped with traces of bromine in order to benefit from the great reactivity of this element towards gold. The gold bromide thus first formed is then transformed into a gold chloride due to the greater oxidizing potential of chlorine. This is accompanied by the regeneration of the catalytic amount of bromine. The duration of this chloridation is very short, from 30 minutes to a few hours, and the consumption of chlorine is very small due to the previous leaching of base metals. If silver is present, the chlorinated mass is taken up with a brine from 250 to 300 grams of salt per liter, in order to ensure the solubilization of the silver chloride. The pregnant solution is then circulated over carbon for precious metal stripping, and the accumulated values are recovered by the standard electrodeposition. The sterol is rinsed and the brine is concentrated and recycled. Cases where the oxidized ore, depleted of base metals, contains metals of the platinum group, the circuit for the recovery of these PGM is similar to the previous one, except that the temperature of chloridation is much higher, at 600 degrees Celsius. Also, the leaching after chloridation is done with hydrochloric acid. The efficiency of this system is absolutely remarkable. A recuperation at the level of 98% of platinum being achieved with an ore at 1 ppm of this metal. The disposal of brines and the recycling of water, along with the use of activated carbon as metal accumulator, is identical to the gold collection circuit, and leaves a sterol without capability of lixiviate generation. Nichromet approach to base and precious metals recovery presents many advantages. The base metals, even at trace level, appears as an asset rather than a liability, contrary to what is found with gold extraction by cyanide. The flotation of the ore is much easier and efficient if the mixture of all sulfides can be collected together. There are no penalties for mixed sulfides, as it is typical with smelting operations. Both base and precious metals can be recovered from the same overall circuit. The levels of recovery for both base and precious metals are very high, while the times of reaction are short. The energy consumption is significantly lower than those observed with pyrometallurgy. The environmental impacts are minimal, with inert and stable tailings. Capital and operating costs are 1/3 of equivalent processes based on pyrometallurgy. Welcome to this presentation of Nichromet's extractive technologies. The last 7 years, Nichromet Extraction Inc. has been involved in a research and development program oriented towards problem solving in extractive metallurgy. This orientation has been motivated by difficulties encountered with several refractory ores, either sulfides or oxides, when recovery of the metallic content was attempted by conventional approaches. Environmental considerations were also involved in this search for new avenues in extractive metallurgy, some existing processes being known for their very negative impacts on the environment, particularly with sulfur-bearing ores. Degradation either by hydrochloric acid or elemental chlorine was selected as the preferred approach to metals extraction. The reasons for this choice are the high reactivity of these agents towards metal oxides and the high solubility of the resulting salts. With few exceptions that can be corrected easily by ionic strength adjustments, such as with silver, lead, copper, and iridium, all chlorides of precious and base metals are very soluble in water. We will now describe the results obtained with the refractory oxides. The first type of refractory ore studied has been the laterites. Laterites are metamorphic minerals resulting from weathering action in tropical or semi-tropical climates on a variety of rocks, such as olivine or serpentine. Through complex mechanisms, some entities are solubilized and reprecipitated at different levels, allowing leaching and buildup of products. Some of these species contain cobalt and nickel. Generally, but with substantial variations, the top layer of laterites, limonites, is very rich in iron, low in magnesium, a few percent at most, and can contain nickel and cobalt at the level of up to 1% and 0.1% respectively. At a deeper level, a different composition is found. With this saprolitic level, the iron is much reduced, in the range of 10 to 20%, while the magnesium as MgO reaches values of 15 to 30%. The nickel is also noted to have a concentration above 1%, while cobalt values are somewhat lower than those found in limonite. The refractoriness of such ore results from the presence of relatively large amounts of magnesium and aluminum not compatible with existing technologies. There is a great number of processes reported for the extraction of nickel and cobalt from laterites. They can be regrouped in 5 categories, depending upon the reagents they used or the conditions under which they operate. Said processes can be conducted in autoclaves under pressure and high temperature, or in vats at atmospheric pressure. The leaching can be acidic with sulfuric acid or hydrochloric acid, or basic with ammonia. The ore can be submitted to a reduction prior to leaching, or used in an oxidized state. The circuit can be a closed circuit, allowing the recycling of some of the reagents, or an open circuit without any recycling. Finally, the process can rely on high-temperature steps, such as seen with the production of ferronickel or in solution at near ambient temperature. Taking into account the problems encountered with current technologies and new avenues made possible by recent developments in the areas of composites and refractory materials, Nichromet has selected acid leaching at atmospheric pressure with hydrochloric acid with a partly open circuit as its preferred approach to laterite leaching. We can now see the overall circuit that we shall examine in detail. The agent selected for leaching, hydrochloric acid, is a relatively expensive acid when related to sulfuric acid, which is cheap and readily available. In fact, each acidic proton on hydrochloric acid is 5 times more costly than an acidic proton on sulfuric acid. This is why it has been decided to generate the required hydrochloric acid in situ by the reaction of sulfuric acid on an appropriate salt. When sulfuric acid is reacted with a chloride, the resulting product, besides hydrochloric acid, is the sulfate of the corresponding metal. There is a variety of different chlorides that can be used to that purpose, and the selection can be done taking into account the existing of markets for this secondary product. The production of a chlorine-free fertilizer, for example, is of real significance because of the importance of the product. The use of naturally occurring mixed chlorides, such as camelite, would lead to mixed sulfates such as leonite or langbeinite, 2 well-known fertilizers. Therefore, the generation of the hydrochloric acid in situ is accompanied by the production of secondary products of commercial significance that can contribute to the profitability of the process. Some of the potential reactions for the generation of the hydrochloric acid are endothermic. Therefore, energy must be fed to the system. The reactor to achieve this reaction is fueled by coal, and the reaction is performed by indirect heating, liberating hot gaseous hydrochloric acid of very high reactivity. A waste heat boiler recovers heat that will be needed at other parts of the circuit. The energy consumption will vary with the nature of the laterite, but will be of the order of 250 kilograms of anthracite per ton of laterite on a dry basis. Reaction of hydrochloric acid with laterite is an acid-base reaction to some extent. For that reason, it is useful to separate the laterite into a magnetic and non-magnetic fraction prior to this digestion with hydrochloric acid. This has been found feasible with most laterites, with a distribution in the 40 to 50% range with each fraction. The magnetic fraction, richer in iron, silica, and chromium, is more acidic and is therefore reacted first with the hot hydrochloric stream from the generator, the reaction taking place at a temperature well above 100 degrees Celsius. About 50% of the hydrochloric acid is reacted at that stage. The hot chloridation, there remains a stream of unreacted hydrochloric acid, which is scrubbed with water to generate a solution of hydrochloric acid. The partly chlorinated magnetic fraction is then combined with a non-magnetic and much more basic fraction, richer in magnesium and aluminum. This mixture is vat leached at about 90 degrees Celsius with the water-scrubbed hydrochloric acid. This arrangement has the advantage of contacting the more basic fraction of the laterite with the weaker acid obtained after the hot chloridation. In that fashion, a near complete reaction is obtained, the pH of the reaction mixture being in the range of 0.5 to 1.0 after 4 to 6 hours of reaction. After the vat leaching, a separation of phases is needed in order to recover the pregnant solution from the residual solid. This can be done by standard techniques, such as belt filter or centrifuge. It is essential to rinse the cake on the filter by at least 2 displacements, so as to recover all of the leached material and leave a waste containing no soluble entities and no capacity for the generation of lixiviates. The pregnant solution contains more than 90% and generally about 95% of the nickel and cobalt present in the starting ore. To achieve this level of extraction, a very significant part of the starting ore has to be dissolved. Typically, 80 to 90% of the iron, aluminium, and magnesium present. The volume of the solution, with a slurry of about 25% solids at digestion plus rinsings, is from 1 to 2 cubic meters per ton of ore. Since said ore has a nickel content of the order of 1%, the concentration of nickel is at the level of 0.1% in the pregnant solution and cobalt, 10 times smaller. The following step aims to achieve a concentration of nickel by 2 orders of magnitude, so as to be able to liberate the metal by electrowinning or other methods such as reduction by hydrogen or deposition via the Mond process. Also, the other elements that are the main consumers of hydrochloric acid, such as iron and aluminium, can be involved in hydrochloric acid recovery by hydrolysis, while magnesium chloride will need sulfuric acid treatment. This concentration of nickel and cobalt from the pregnant solution can be achieved by ion exchange resins or solvent extraction. The resin used, Dowex 4195, will retain the trivalent iron while the bivalent iron is easily eluted. Therefore, before contacting the pregnant solution with the resin, the trivalent iron is reduced with elemental iron. The collection of nickel and cobalt over the ion exchange resin is done at pH 2 to 3 by circulation through 3 columns in series, with monitoring for nickel at the discharge. When loaded, the first column is put out of circuit and rinsed with slightly acidic water. Then, nickel and cobalt are desorbed by 2-N-ammonium hydroxide, and the column is regenerated by hydrochloric acid treatment. The concentration of nickel in the basic solution is in the range of 5% by weight. It can be precipitated as oxide or reduced to metal by standard reaction. Separation of nickel from cobalt can be done by solvent extraction as currently practiced with Cyanix 272. The residual pregnant solution, after the removal of nickel and cobalt, contains the iron, manganese, chromium, aluminium, and magnesium dissolved during the lixiviation in the form of chlorides. Of these chlorides, all can be hydrolyzed to hydrochloric acid and their corresponding oxides except magnesium chloride, which requires a much higher temperature to do so. 2 options are to be considered at this point. If the starting ore is very rich in iron and relatively poor in magnesium, as it is the case with limonites, the recycling of the hydrochloric acid can be done with a mixture of chloride incorporating the magnesium chloride, sulfuric acid being added to make the magnesium soluble as sulfate. Then, by water leaching of the residual mixture of oxides, magnesium sulfate can be recovered. If, on the other hand, the starting ore is rather rich in magnesium and low in iron, then the solution can be freed of iron by pH adjustment and concentrated to obtain the purified magnesium chloride. This magnesium chloride can either be recycled to the production of hydrochloric acid, as indicated before, or used as a source of magnesium derivatives, such as magnesium oxide. The Nichromet circuit is highly adaptable and can address to a wide variety of laterites with compositions from 5 to 50% iron and from 0.5 to 20% magnesium or aluminium. The generation in situ of the leaching agent, hydrochloric acid, from the action of sulfuric acid on a salt gives a great flexibility on the starting products. The selection of the salt can lead to secondary products of interest, such as fertilizers, magnesium chloride or oxides, salt, cake, etc. On a general basis, the value of the secondary products will cover the cost of their manufacture, including the energy involved. Therefore, the hydrochloric acid comes free as far as the costs of supplies and power are concerned. Consequently, the nickel-cobalt recovery from the starting ore benefits of amortized hydrochloric acid and waste heat for leaching operations. The operating costs related to supplies are reduced to a minimum, particularly since up to 95% of the hydrochloric acid involved in the leaching can be recycled with ease to the system. As for magnesium chloride, it can be recovered as a sellable product or recycled to the system for hydrochloric acid production via the action of sulfuric acid, magnesium sulfate being the end